briefly. Recite, review, check whether you know the chorus equations of the core, the defining equations from which ultimately everything can be built. Let's put these in Google. Let me see what fraction people know each of these. Sahyu, can you help me mark let's say the right answers in green or whatever? Okay, first off, kinematics equations, define. When I say define, everything is gonna be defined. When I say define, I mean give the defining equation. You can describe in words. I don't want that. I don't want that. Also, please, except for the 5 people who never listen to instructions, the 95% of y'all, I do not want people to type out F-O-R-C-E for force. Just say F, damn it. Okay? I know this might be difficult, a difficult concept to represent an idea with a letter. Come on, baby. Don't type out words. I want a simple equation, please. Okay, define kinematics terms. Define velocity. Give me the central equation that explains what velocity is. B, displacement. Hey, do this without your notes, by the way. What I was blathering on about at the beginning is if you know these things, then you know your vocab words. If you are doing this with your notes, a cheat sheet, the internet, then you're just checking to see if those things know the terms. You don't really know if you know. Velocity, displacement, acceleration. From these definitions, everything in kinematics can be built. In dynamics land, Newton's second law. And as I said, all of these are the equation, hint, hint, hint. Weight force. Friction. Just put them both together, static and kinetic, write the simple form. We added this to this module, but it all logically goes together. I'm going to say spring force here. Kimmy, give the equation. Do not give in words. Do not spell out anything. Give a simple equation using the standard symbols. I'm looking for like typing 4 characters or so, not lots and lots of characters. Okay. I'm missing one. Newton's second law, friction, weight. No, that's it. Okay, rotation, angular velocity. Angular velocity, angular velocity. This isn't a single term. This is the equation connecting angular and linear velocity. I'm missing one here. How about, what's another term that we defined? Screw arc length for now. What? I didn't do centripetal acceleration with you. Right? No, I want to talk rotation just for a second. We're not going to do the foundational stress strain Young's modulus, but I'm missing one for rotation, foundational one. Screw it. Now work. Kinetic energy. Eleven terms. I think there's a 12th that I'm forgetting. We'll learn one more idea today. It's not really an equation. We'll talk about spring energy. There we go. So yeah, there will be a 12th term, but I think this is basically the entire semester, the foundations for the entire semester, the thing that I would hope that given how we've used these terms for months, that each of you has attached meaning to and can memorize if you so desire, and you should desire. Okay, let's see how many people have got these core defining equations. Again, I strongly encourage you, if you can't do these without your notes, you don't actually know them, don't fill these in just for the sake of filling them in. Get a feeling for what you need to study. Write down what you don't know and then go learn these. I will strongly encourage you also to look at what letter is which. I'm just going to mark you wrong if you put the wrong thing in the wrong box. I'm done with trying to piece together people who can't read. This is letter A, B, C, D, blah, 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 blah. I did do centripetal. I did do. I cut out angular acceleration. Oh, I'm so clever. Centripetal acceleration should also be on your list of things to know. V squared on R acceleration. I don't want to spend too much time. I don't want to spend like any more time on this. This is to see how you guys are doing and to encourage you guys to go back and learn things. And I'm gonna say time's up. Okay, in case you don't have these, first off, have these. But in case you don't have these, here are the quick answers. There are multiple ways of writing these. You've seen that 1,000 times. Here's one way of writing these. Velocity is defined as the rate at which position changes. The change in x over the change in t. A fair number of people say x over t. Wow. No, not really. X is where you are. Delta x is where you change by. Displacement, I would say delta x is final position minus initial position. Acceleration is defined by change in velocity per time interval. Newton's second law, net force equals ma, not mg. Weight equals mg, not ma. Both frictions are related to mu n. As you hopefully remember, static friction is anything up to that limit. I'm really writing the maximum. For kinetic friction, you've got that just simply there. If you wrote mu n, you're on track, hopefully. How did I call spring force? I think I called it Fs, right? Negative K times change in length of the spring. Angular velocity is the rate at which a central angle changes. V equals R times omega. And kinetic energy, not to be confused with spring constant. Oh, big letter up there. I don't want to spend time discussing these. We can when we actually do review week. It's not a week, review day. Review week of lab, review day in here. But for God's sake, I need to look at the syllabus, whether I said the course calendar. I don't remember if I gave a week for review or wanted to cover one last energy practice on that Monday. Screw it, let's move on. My point is, and I do have one. Oh, I would have accepted anything. I often use the letter D for delta. On some computer operating systems, it's option J. That, if you wrote anything X, I took that as you probably knew what you're talking about in terms of change in, not just divide any old meters by any old seconds. Kimmy, this is based on what we learned all semester, as I've been saying all semester. That's what cumulative means. This is a cumulative final. Okay, let's hop into energy land. Energy, what we did last time is we connected work done, 1/2 force times distance times possibly 1, -1, or 0, cos theta. We connected that with the changing kinetic energy, 1/2 mv squared. Today I'd like to practice this a couple of times, a couple of dozen times, see how it goes, and get a better feeling, hopefully, for what energy, kinetic energy, and work done is. Since we have only one force, one conservative force, one easy to calculate work force, I'm either going to give you a magnitude of a friction force or a general applied force, or assume that you can plug in m times g and do with weight to find the work done by weight. So we're going to keep it to just the forces I either give you or that you already, God willing, know rather a lot about. Remember the hint from last time, if we're talking about gravity, is weight, work, doesn't care about left-right motion. So the distance part of weight, you only need to consider the vertical distance. You can prove that with trigonometry. Look at what distance cos theta means, or you can just take my word for it. I'm not going to go into the proof in here. It's one line of trig, but trig scares people. So let's do exercises. Suppose I go up a mountain, as I like to do. I wonder how many joules of energy it costs. I'm going to tell you that my mass, with my backpack and everything in it, is about 65 kilos. I'll give you some information to make you think about the terms that make sense here. I'm going to tell you that it's a pretty steep mountain as far as mountains go. 10 degrees is actually pretty darn. What the hell? I happen to know this is going to be a crazy steep mountain. I happen to know how to climb. This is like hands and feet. That is the angle of the mountain, by the way, not necessarily a theta that you would possibly plug into an equation. Hint, 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 hint. I'm going to change my height. Have I been calling this H or Y? I think I've been calling it H. I'm going to change my height by 200 meters. I'm going to trudge along at a constant, more like 1 meter per second. Tell me, if you can, tell me, what letter are we on? L, L, L? How much kinetic energy do I start with? M. How much work does gravity do? As I hike. And, ooh, I need to calculate this fast. No, you don't need that. I don't need to give you that number. You can deduce this. How much work does friction do? You can find this based on strictly what is given. I'm not giving you a magnitude of the friction force. You don't need it. What else can you find? What else can you find? What else can you find? I think that's it. I'm going to answer the first question that is asked. Your velocity is steady. Yes, your velocity is steady. And the second question that is going to be asked is there friction? I mean, yeah. Okay. Take a stab. Ready, set, go. And if you get imaginary numbers, no, you didn't. You didn't get imaginary numbers. Oh, it's silly to write K and then write work. I don't need friction. I don't need. Yeah, good, right, yeah. Okay, 2 minutes. I got the vast majority of the class in. Finish her up. Oh, hey, uh, last Wednesday, hold on a second, I want your attention. Last Wednesday, yester class, I came up with a brilliant idea for the participation points. Last time I attempted to grade by correctness, I coming in at the end of class, if there's a goof in the being there or not, maybe a connection fails, maybe everybody entering at once screws something up, but I had several students say that their form didn't refresh or something didn't work. So I threw that idea out. But I despair of the educational system when people don't know math. People not knowing physics, well, that's my job, helping that out. And good God, I've helped a number of people with that. I don't look down on you guys for not understanding something in here, but completely ignoring instructions, that pisses me off. You guys should be able to listen to something said many times and listen to it. So I have decided for the following thing for your participation points. Hopefully this is fair. One is there are a number of students who've been logging in at the beginning of the class and then going to sleep or, oh, but their name is in the participation points column and they do absolutely jack participation, absolutely nada. I'm not going to give points for that anymore. Just sitting doesn't participate, so you don't get participation points. It's not called sitting points. And number two is I'm going to scan through and people who are very obviously completely ignoring, let me just put it simply, people who are pissing me off by completely ignoring the instructions, get 0 points for the day. They are not listening. So if we're going to do this, and I am going to do this, if you are at all unsure of what I am asking, of what letter something is going in, of a format that I am asking for, you have to ask. You can't just guess, right? Or you're going to lose your entire participation points for the day. Don't just BS it. Ask if you don't know. I would hope this is fairly obvious, but based on what I've seen in the participation form, apparently we've got, well, more than a dozen students in both classes that really don't know what letter is written on the board or something. I don't know what's going on. So are you guys okay with if you do nothing all class, that is not participating, and if you royally piss me off by completely ignoring instructions, that is worthy of being smacked down? Great. That's my new participation points routine. Since I didn't announce that until today, this will only be the last of the 4 participation points sections. Participation points 3, that's already done. That's already going in. That was under the old rules. I'm going to put this on under participation points 4. And next year, next semester, that'll be all 4 sections for next semester. Okay. So all of next semester's participation points will be based on doing anything at all. You don't have to do everything, but you can't just completely check out and not royally pissing me off by totally ignoring my instructions. Okay, so let's do it. Oh my sweet baby Jesus, every single person that is not zoning out did do L, and I do believe with one exception, it's all correctamundo. The one exception is a couple exceptions. Okay, so the one exception, how do we measure work and energy? Joules, what's Newton's measure? Force. Force and joules are different things. So all 3 of these answers should be written in joules, not in newtons. Not in meters per second either. Okay, so the correct answer for number for letter L is 33-ish, 32 and a half. How do we do this? Half mv squared. Obviously, I think just about everyone got that. Please note, how much does kinetic energy do we end with? The same amount. In one of the problems that I gave with the roller coaster, the final motion energy came from the work done by gravity, right? Yeah. So we set half mv squared equal to the work done by gravity. Here, I specifically said, and we don't accelerate. We go at constant speed. Don't memorize kinetic energy equals work. Think about what is going on. If velocity is not changing, kinetic energy is not changing. Okay, part M, part dos. How much work is gravity doing as I hike? Well, methinks my displacement is up a hill. My force of gravity is down a hill, down. Are we positive or negative work? Is gravity helping or hindering us? Hindering. Gravity is opposing our motion. Only half the class put the minus sign. Watch out. Signs are important. Am I adding energy? Gravity is not adding energy. As I go downhill, gravity is helping me. As I go uphill, it is hindering. Negative 130,000. Negative 130 kilojoules. Or if you plugged in 9.8, 127,400. Okay. So force times vertical distance with a minus sign, yeah? N. Riddle me this, Batman. Riddle me this. Am I changing my kinetic energy? What did we just say? Am I changing my kinetic energy? No. So what is the total work done on me? 0. If you know that gravity is sucking some energy out of me, then I think friction, the traction of my boots on the ground, had better darn well be giving me that energy to hike. It is friction which allows us to hike uphill. Remember what we talked about? That friction is what allows you to move along, to walk, to drive a car, whatever. Without friction, you just spin your wheels. So friction is the propulsive force. positive 130,000. So again, the correct answer is about 33, about negative 130,000, about positive 130,000. Question me. Which direction, when you're walking uphill, is that propulsive friction acting? Yes. And which direction are you displacing? Uphill and uphill are the same direction. I said the work done by weight doesn't care about sideways motion. I didn't say work never cares about sideways motion. Just weight is the only thing you can always assume I only care about up. But I didn't give you the force of friction. You don't need the force of friction. If you had the force of friction, you would also need to find the length of the hypotenuse. I only gave you the length of the opposite side. I only gave you the height change. Yeah? Fernando, please. What does theta mean in that cosine? What is the angle about? Nope, that is not how I define theta. You remember, Isa? How did I define theta? The angle between what and what? The what? What is the angle when we have force displacement cos theta? Theta has a meaning, and as I cautioned y'all, it's not just any old angle. You have to think about what theta means for each force. Theta is the angle between the force and the distance moved. Theta is the angle between the force and the distance moved. I also hinted that I will never give you a problem in which it's not 90, 180, or 0. But forget the gaming the system. The meaning of that theta is not just some angle that you see in the problem. Every force can have a different theta. Displacement uphill, duh, right? There are different forces acting. The normal force is perpendicular to the plane of the hill. That's why normal does no work. Friction force is up the hill, moving you along. That's why the angle between those two is 0. Weight is down. There's a 130-degree angle there, but 120-degree angle there, but I said ignore that. We're just going to talk about the vertical distance for that force. Then the 130,000 joules is then going straight up. Joules don't go up or down. So I'm saying is it because of 90 degrees? So the funky bunch thing is, where did this theta, what did this theta, how much did I need this theta in part M? I didn't need it at all. As it turns out, steep hills and shallow hills require the same amount of work to get to the peak. If they're the same elevation, it's the same amount of work. You can do a long hike over a shallow incline or a steep hike over a short distance. If you get 200 meters up, the steepness of the hill is irrelevant. So it's not that you need to move straight up. Whatever hill you're on that you move, that force propelling you, which is friction, ultimately, if you're moving at constant speed, has to be the thing that's giving you the energy that the gravity takes. Let's do another problem and think about this. You're thinking deeply about the meaning here, which I love, which is great. And I hope you're all listening to Fernando's question, by the way. This is getting to the core, one of the core ideas behind work. Please keep asking, though. Please keep asking. Anyone else have questions about this setup? Okay, the backside of the mountain is a steep, 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 steep cliff. I fall off the backside. I climb to the peak. Woo! Fall off the backside. How fast am I going when I hit the ground? Use conservation of energy. And we'll assume the ground is level on both sides of the mountain. Again, so question O. Backside of the mountain is steep. The backside is a cliff. If I fall all the way down, how fast am I going when I hit? I strongly encourage you, ignore kinematics and force equations. Practice the energy methods. Anyone visualize the scenario? Yeah? Questions? Can you visualize it? Imagine what's going on? Okay, apply the one and only concept we've been doing. I should say, how fast am I going just before I touch the ground? Once I touch the ground does work on me to stop me as I splat. But that's not what I'm asking. I'm asking, how fast am I going just before everything goes black? Fernando, did I ask the question you were answering? Did I answer the question you were asking? Mhm.
Giving it maybe like an assist.
Mhm.
Whereas like before you were saying one is the 90. Like no, one was the one this way, right? Not high, but like 0.
Mhm.
This would be up.
Yeah, it's not the angle that you're moving.
I was thinking more position rather.
It's not the angle of the displacement. It's not the angle you're going at. It's not the angle you change by. It's what is that angle compared to the force.
The relationship.
Yes. I mean, force times displacement, right? Those are both vectors. They have directions. How far do I have to go if I'm going uphill and the force is uphill? There's no angular change between uphill and uphill. I mean, it's a 0-0 triangle. No, 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 no. Angles don't measure hypotenuses. Angles measure, 30 degrees measures the inclination. Yes. No, 30 degrees hypotenuses are measured in meters, not angles. There's a reason that I'm saying skip the trig. Trust me on this. I could prove this, skip it, trust me. With weight, and only with weight, displacement, we just care about vertical up and down, regardless of the hill. And again, for the principle for n, how I encourage you to see it, to look at it, is did my kinetic energy change? There's no change in my kinetic energy. Total work must be 0. Friction must be giving me that 130,000. The gravity sucks out.
That's the one.
Exactly. My bank account never changes. I got 30 bucks, 27 bucks in my bank account forever. I guess I spend as much as I earn. The work done by friction, my paycheck, is equal to the work done by gravity, my expenses. Miles per hour. What you talking about? Foo, we don't use miles per hour in here. About half of you. Okay, here's the principle. Well, I'm a professor. I'm not a principal. Here's the principle. Where's the motion energy come from? What force is causing it? If you're freely falling, wait, no, we haven't talked about potentials yet. We'll talk about that later. Weight is causing you to accelerate. So I would say the work done by the weight force is equal to how much kinetic energy you gain. Now, as you saw in the first part, in these three questions, I only start with what it was, 20, 30 joules of kinetic energy, and I then gain 100,000 joules of energy going in and coming out from gravity. Do I even need to care about those 30 joules? No. I'm barely moving up the hill at that 1 mile per hour, 1 meter per second. Who cares about that? So I'm going to say you're basically at rest. I should say the change in your kinetic energy equals the work done by gravity, but I'm just going to say your final kinetic energy is really freaking mostly entirely just about the work done by gravity. So number O, here we go. I would say the final kinetic energy comes strictly from your mg delta y. Mg delta h. What have I been calling it? HYH. Is this positive or negative? Which way am I going? Which way is the force? Down, right? We're talking about the weight force. So I should use positive numbers for all this. To be specific, delta H in this case is actually negative. I have gone up 200 meters and then I go down 200 meters. Down is the negative direction. If I'm looking at the magnitude, I'm saying 200 meters. Okay, pew, m cancels m, v squared equals 2g. Well, magnitude is really just for the h part. V equals square root 2g delta h, which is to say 2 times, screw it, 10 times 200 equals about 68, 63-ish. Okay, please turn to your neighbor and explain what's going on here. It's the same process we've been doing. It's the same process we're going to do. If this clicks, if this makes sense, you'll see that everything we're doing today is really, really straightforward. It's not as confusing as it seemed at first. So please turn to each other and argue about what the hell Tucker did and why did he do it. Where's that go?
What we're doing is we're using quickly. However, how everything except the compression. So you get this by itself. Simple math, very, very simple math, sixth grader. By the way, this is supposed to be H. I don't know how, I don't know where. Yeah. Yeah, B is the not equal B. Yeah, no, this is supposed to be an H. I don't know what, I don't know, well, B does equal B. Yeah, but I don't know why it's supposed to be H. But yeah, so the velocity. I pre-ordered stuff, like the squared stuff. Get rid of the, anyways. Like I already removed the square. So I put it square here. And then obviously the gravity's 1.8, 200. I got 3,920. And square rooted it. Velocity equals 6.2.6. 52.6 meters per second. Which equals to 2 centimeters. Right, I was just honestly, I was not expecting But it looked right, like when I was doing it, I was like, wait, this is like, to be wrong. That was kind of nice. Oh, this is wrong. I did not. I just use this. I use.
All right, let's bring it back together. Questions from the class. How are you feeling about this? Questions, 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 questions. Pregúntame. Frag mich. Did it. Nadie? Let me, instead of just judging based on your expressions, which everybody, I think, at this time of the semester is pretty did. Google question P, I just want a rating from 1 to 5. Please type the number. Type only the number. Do not spell out the number. Do not, I don't know, just type a number from 1 to 5. 5 is move on, Tucker. 1 is I don't even know the equations, I'm so lost. Give me a rough sense of where you are. Now we'll take majority rules. Oh my dear Lord. Okay, well, I've got someone who's getting 0 participation points because they can't follow simple instruction. It feels so much better now. I'm not going to moan about it. I'm not going to complain about it. I'm just going to kill their participation. Yes. Because the work is positive, but I'm going down. I mean, displacement is negative, but I don't want to double count a negative sign. I don't want to have a negative sign. I mean, really, weight is down, displacement is down. It's a positive, negative, negative. Okay, that's a 4 out of 5. I'll take it. I'm not moving on to give you new forces. I'm not going to give you on to give a mu equation. I'm going to give you one new idea that ends up being another way of seeing this. Yeah, you can express this in an equation, but if you just write down the equation and don't think through it, you're screwed forever. You'll never get this. So let me encourage you, please, brains on engage. Here's an idea. If you get the idea, you will have great magical powers. We're going to then apply this idea to the physics we're doing. It's just a different way of seeing the same thing. There is a new term I'm going to call potential energy. And I'm going to say potential energy is how a force stores energy in something. We're going to talk not about work done by gravity, but about how much energy gravity could give you or take away from you. Yeah? So I'm going to have a second form of energy. It's not a new form. It's really just work, encapsulated work, distilled work in a single line. And the idea is the change in potential energy. As I go up, I am gaining potential energy. Work is negative, screw that. Gaining potential energy as I go up. That potential energy could become kinetic if I let the object fall. So think of potential as stored energy. As I go up, am I increasing or decreasing my storage? I'm storing it. I'm increasing my potential energy, the potential to become kinetic. What happens when I go down? Is my potential going up or down? Potential energy is decreasing. There is a straightforward, simple, easy peasy lemon squeezy equation, which is to say potential energy at a point is mgh. Bam. Wait, mgh? It is very common to miss at the beginning, to mistake work and potential energy. They are two sides of the same coin, but they are different sides. And if you do replace one with the other without thinking about what you're doing and accounting for that, you will screw up the problem, okay? So, please, let's go over 3 slides to explain this concept deeply, deeply, truly. And then we will apply that to this left, right, and center. It was on my laptop. I just need to transfer this over. You've got 3 minutes of wiggle time. Chill out for a second. I got to send this over from my other device.
So, there's no-
Hair drop. Ross's iPad.
I think so. Tomorrow. But, right? You know, but also, for some reason, there's a red portion. So,
Oh my God, that took 30 seconds. That was silly of me. Well, I just am a big silly, I guess. Okay, so the topic here, we will practice this. We will apply this more. I see it is 4 o'clock. So I'm going to introduce this. We're not going to have time to apply this to the same problem as before. We'll pick that up at the beginning. But hear me out. I'm going to give you the idea behind it, the concept behind it, the thing that I will have 50% of the test on behind it. Remember, I care about you knowing what you're doing, not just plugging in numbers. Concepts are important. Okay, so we're going to talk about how there are forces that have a potential energy and don't, and the meaning of the equation behind potential energy. So you can reason about it, not just have something on your equation sheet that you misapply and then miss things with, right? As I was yakking about at the beginning. Force times displacement times cosine theta can apply to any force, right? If you move and you have a force, you can always do that. Any force does, well, it might be 0 work, but if there's a force acting on something and that object moves, you can calculate the work done by that. And so any force can do work, but there's kind of a difference in the sort of work that friction and weight do. Suppose we've got kinetic friction. I'm scuffing my feet across the floor. Where is the energy? Where is the work done that I am scuffing on go? Do you guys know what form of energy that takes? Rub my hands together. What form of energy am I creating? Am I transferring it? Friction is the force. What kind of energy am I creating? Ding, 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 heat, thermal energy. Yep, 2 words for the same thing. I'm heating up my hands, right? Right? Okay, so, work done by friction often transforms energy into a thermal energy, which I call internal energy. And screw that sucker. It is very hard. You need a fancy pants machine to turn heat back into kinetic or work or whatever. You need a boiler with a piston and stuff, an engine. It is something that can take heat in and get something useful out of it. We're not doing the physics of engines in here. When we get heat energy is considered loss. We're not going to be able to recover heat energy. There is no potential energy of heat. We do not store energy with friction thermally. Work done by weight is returned. What'd you learn about an object that you throw up and comes down to your hand? How fast is it moving? Guys, remember this? You throw an object up, you catch it at the same height, moving faster, slower, the same. It's the same speed, opposite direction. Remember? Okay, so the kinetic energy of the ball, when it reaches the same height, when the height goes up and then goes down, the kinetic energy is the same. All of your, kinetic energy gets returned. The work done by weight is returned to the object if the object returns to its starting height. We have a potential energy of height, of gravity, of weight. Here is a definition. A conservative force is not just one that conserves energy. Energy is always conserved. Remember, conservation means stays the same. Conservative force conserves mechanical, useful energy, kinetic and potential, and so on. So a conservative force is something that depends only on where you are. And if you go back to your starting place, the energy that is taken is given back, or the energy that is initially given is taken away again. Right? If I go up and then I come down, gravity does positive work. Sorry, gravity does negative work, gravity does positive work. Yeah, you seen that? Like in the problem we just did? Okay, so, weight and springs are the two forces that we've done in this class. And we're going to see, I am going to add in spring energy probably on Wednesday. We're going to add in spring energy, and we're going to see that if I stretch a spring and then let it compress, I can get the same amount of energy as I put into it by stretching it. If I compress a spring and let it spring back, I can get the same energy out that I put into it. You'll never believe this. A force that is not conservative is called non-conservative, big shocker there. It should be called a liberal force, but it's not. And one way you could say what makes a force non-conservative, other than just saying it's not conservative, is if the work done depends on the way you go, then that's non-conservative. For instance, I scuff my feet on the floor, positive or negative work? Is friction helping me or hindering me as I'm scuffing? Hindering, right? Is friction helping or hindering me as I scuff the other direction? Hindering. I lost energy both directions. My total was not returned. I didn't get minus then plus energy, work. So if I went further and then came back to my starting point, the force would be even, the work done would be even more. If I went a very little distance, the work would be very little. So even if I return to my starting place, the work done is more or less, it changes. Whereas with gravity, it doesn't matter how far you go up. If you come back to your starting height, you're moving just as fast. You got the same amount of kinetic energy. The stored potential comes back. And here's the big slide. Here's the big thing. Anytime you have a conservative force, you can associate this with a potential energy. Potential energy ain't nothing but the work done by the force viewed as a stored energy instead of a taken away or given external work. Symbol, it's kind of stupid. You'll see sometimes in some books, some websites, they call it PE and kinetic energy is KE. I will use in here, if I recall correctly, your textbook. Yeah, I'm sure your textbook uses capital U. It's all about U. Signs. Does gravity help or hinder as I go up? What's the sign, positive or negative of that work? But as I go up, I'm storing potential energy, right? My potential energy increases when the work done is negative. The change in your potential energy is not force times displacement cos theta. The change in potential energy is negative of that. Because if gravity is sucking energy out, we're imagining removing energy as storing that in some different form. Who has a savings account? Yeah, well, with this economy, with how shafted your generation is, I'm not shocked by that. Imagine, if you will, having both a checking and a savings account. Think through this with me for a second. You transfer money out of your checking account. You store money in your savings account. Your savings account is potential energy. Kinetic energy is your checking account. You store energy in your savings account. Does your savings account go up or down? Up. You're transferring into the checking account. Yeah. What is happening? That transfer, is that increasing or decreasing the account that you're doing something to? The checking account. What is happening to that? Is that a positive or a negative work? A negative change, a negative applied to a kinetic energy is a positive change in potential energy. So, negative sign. When we're viewing it as stored energy, we are lifting an object up, we are storing the ability to come back as kinetic. If we're viewing it as an external, as gravity as something outside our system, gravity is trying to suck energy out. Displacement this way, force this way, negative work. Right? Right? Last point here, the delta. Note, real briefly, I have said every time as you have work done, work changes your energy. Absolute value of energy is unknown and unknowable. Energy, potential energy itself has no 0 point in Newtonian mechanics. You do not know how much energy you have, potential energy. It does not matter how much potential energy you have, because the only thing that matters in classical mechanics is when potential energy changes. Let's say this ground is height 0. The formula for potential energy, gravitational potential energy, is mgh or mgy, and weight times vertical position. If this is 0 and I go up 1 meter, have I gained potential energy? I have gone from position 0 to position 1. What would I plug in for y? I've gone up +1. Yeah? Okay, now suppose I imagine that the actual ground level of the building is 0. This is no longer position 0. This is position, I don't know, 10 meters. We are 10 meters above ground level. I don't know, I'm making this up. What height is this at? 11 meters, right? Okay, if I say that I have gone from mg times 10 to mg times 11, that's the same change in energy, right? The absolute value, the starting point where I say y equals 0 is irrelevant as long as you're consistent. If you say that this height is the 0 point of potential energy, and I drop a ball off the ground and then say its final position is the 0 of potential energy, you screwed up. As long as you're consistent, as long as you use the same where is y 0, you're done. Make a note of this as you do problems, as problems get complex. You remember you assumed y is 0. I will very often have the convention of the floor level if we're doing something just inside a room, or ground level if you're doing something outside. But I want to make the point that it doesn't actually matter. As long as you define a reference, potential energy changes relative to that is perfectly well defined. So again, work done. If I go up and the force is down, mg times delta y is negative mgy, mg change in y. Potential energy changes by the opposite of the work done. If I go up, I store mg times the change in y. I made this point exhaustively, I'm going to move on. You could define, I made this point exhaustively, I'm going to move on. You can define anywhere as 0, y equals 0, doesn't matter, all that counts is the change. So we'll very often say the origin, remember origin is not starting point, origin is where do you consider position 0. If we set position 0 is the origin, potential energy there is 0, then you could just say potential energy at a time is mgy or mgh, whatever you're using for height. Easy peasy lemon squeezy, or difficult, difficult, lemon difficult. Okay, when we are dealing with only potential, gravitational potential, they're both gravitational potential and kinetic. If there are no other forms of work done, all you do is say that the change in total is 0. We can solve a butt ton of problems without thinking about the signs by just saying energy might go from kinetic to potential form or back, but the total change, if you add up the initial forms, add up the final forms, the total change is 0. If there's work done, the total change in energy is equal to how much energy you put in with work. But we'll do a bunch of things where there is no work, where there's just a constant amount of work, and the change in potential, the change in total energy is just that, whatever that is. I regret then show how much I find this easier and some people find this harder. I personally really prefer the total energy is potential plus kinetic way. This for me is far easier than thinking about the work done positive negative bit. We're out of time. We'll pick this up on Wednesday. I love you. Goodbye. Any questions? Come on.